Thank you very much for this invitation. It's a great pleasure to be able to talk to you about the image of M87 from the Event Horizon Telescope. I regret that we are not doing that in person. I really enjoy visiting Prague, and both for professional reasons and for private reasons, I often do that, and it's always great to come to Prague. Well, unfortunately, this time we'll have to keep it online. I'm used to giving talks a little more technical than I will try to talk to you today. So I hope I made it approachable enough, but we will see if the number of people will be decreasing during my talk. That will be a clear indication that I have exaggerated, and I will try to talk in a more approachable way. It's also a great pleasure because this is a rare opportunity to wear a jacket. We are working from homes for a long time now, since the beginning of the epidemic. So I'm really happy that I got some occasion, some opportunity that I actually could put my jacket on, and now I look good for at least for a moment. Okay, so let's start. And I will need to learn how to change. Okay, I know how to change slides now. This talk will be divided into 3 parts. So in the first part, I will talk to you about physics, about black holes, about spacetimes, about plasma, magnetic fields, and accretion. But it will be very easy, so please don't run away. In the second part, once you become expert in general relativity and related problems, I will talk more about the Event Horizon Telescope and the technology of that led to the image of a black hole. So when you will be experts in both relativistic physics, and you will be also experts in engineering. So once we go there, we will talk a little bit about images in natural sciences, about epistemology, maybe about some kind of philosophical aspects of that. So I hope that will be quite interesting to you. Okay, so let's start our really quick, really quick part about the physics from a very simple idea of what black hole is. And this idea has to do with the escape velocity. So you can imagine that you have a stone that you throw vertically into the sky. So you just throw it up. And you can expect that this stone will come back, and hopefully it won't hit you in the head. But you can also expect that if you give it enough velocity, if you deposit enough energy to this stone, it will just fly away, leave the Earth, and never come back. That is the expectation. And you can actually calculate what kind of velocity do you need to give to your stone in order to for it to leave the Earth. And this velocity for the Earth is about 11 kilometers per second. So quite large velocity, kilometers per second. This is not kilometer per hour, it's kilometer per second. It's very fast. But you also notice, if you calculate that this escape velocity is depending on m, which is mass of the Earth in that case, and r, which is radius of the Earth in that case. We call this ratio compactness, and you can imagine that for a different planet, for a different object that has larger mass, but say same radius, this velocity will be larger. So if you have an object that is very massive, but this radius of this object is smaller, then this escape velocity will be growing larger and larger. And actually, a long time ago, that was still in 18th century, John Michell asked this question because there were astronomical observations that were showing that the speed of light is finite. So he asked a question, so what if this escape velocity would be as fast as the speed of light? Would that mean that light cannot leave this object? So if light cannot leave this object, would that mean that this object would be entirely black, like a dark star, or like a black hole? Actually, he didn't use the word black hole, but I took this artistic liberty of attributing this black hole to John Mitchell, because essentially that's what he considered. And he did that without relativity, without any sophisticated theory of gravity. Well, it was a little bit sophisticated in a sense that Newton's theory is quite a serious theory. So this is the Newtonian theory of gravity. And this is the equation that you should, I hope at least some of you remember from high school. This is equation describing the force of gravity between two objects of mass m1 and m2 at a distance r square between the objects. So Newtonian's theory of gravity makes a couple of very essential assumptions. And let's say that one of these assumptions is that there is time, there is space, and they are absolute and independent. Time is running, space is constant and absolute. And then the gravity is just a force acting between two massive objects. So this is Newton and 18th century. But then in 20th century, we got to a little more sophisticated, more general theory describing relativity. And this is a equation that you should not remember from high school unless your high school was very special. Otherwise, this equation is only well known to people studying gravity at the academic level. There is a very important assumption that goes into general theory of relativity, into this more general description of gravity. And this is that time and space are no longer absolute, they are no longer independent. General relativity is a geometric theory. It treats space-time, this combination of time and space, as a geometric object. And it uses mathematical methods associated with geometry to describe it. In this sense, gravity in general theory of relativity, this is not a force in the sense of Newton. Instead, gravity is a geometric deformation of space-time, of this combined, intertwined creature that combines space and time into four-dimensional thing that mathematicians call manifold. And you can see that those equations, of course, this equation of Einstein looks a little more complicated, but you can see some structural similarity. So for instance, G, letter G without any indices, this is the gravitational constant. You see this is a proportionality constant in both theories. This letter T with indices alpha, beta, this is a so-called stress energy tensor. This is something that has mass m1 and m2 inside of it. Then this G alpha beta is so-called Einstein tensor, and this is a little more difficult to compare to the force. But what is important to understand is that this is the mathematical entity that tells you about the geometry of the space-time. So this equation looks a little more complicated than Newton's theory, but it's not much more complicated. Well, unfortunately, if you open up this G alpha beta, first of all, so-called Ricci tensor will pop up. This is this R alpha beta guy. I'm only showing these equations because it's a little fun. I'm not trying to make anybody understand deeply the meaning of the equations I'm showing now. And then this Ricci tensor, this R alpha beta, this is also complicated. So you see that within this symbol G alpha beta, there is a complicated creature living. And one thing to notice is that this complicated beast is non-linear. And this is the source of a lot of headache for the people studying Einsteinian gravity, nonlinearity of the theory. So Einstein published his equations of general relativity in 1915. And he was pretty sure that because of this complication in the equations, that it won't be possible to find very simple solution. But he was wrong, it turns out. And very shortly after publication of the theory of general relativity with general equations, Karl Schwarzschild solved these complicated equations that you have seen in the previous slide. He made very strong assumptions. He assumed that the solution should be static, meaning it doesn't change in time, it doesn't evolve in time, it looks the same at every moment in time. He assumed that it's spherically symmetric, and interestingly, he assumed that there's absolutely no matter in this solution. It is a vacuum solution, there is nothing material in it. And he calculated this quantity that is shown here, Rs. We call it now Schwarzschild radius. And it turns out that if you did the calculation of John Mitchell, Newtonian calculation, you would get exactly the same value as Schwarzschild now derived from the complicated equations of the Einstein theory. So Karl Schwarzschild solved these equations, and he noticed that there are very weird things happening in this solution. There is a central point called singularity, where the curvature of space-time is infinite. It's a discontinuity in this solution, and it's hidden behind a surface, virtual surface, that is called an event horizon. And this event horizon surface has a very weird property that you can cross it in only one direction. You can fall into the horizon, but you cannot go out of the event horizon. And there is all sorts of different effects related to stretching, and it is stretching not just of space, but also stretching of time. The time is flowing differently in different regions of the Schwarzschild solution. So this singularity, the presence of singularity and the presence of event horizon, was something very off-putting to people. Einstein himself didn't believe that it could be something real. This is what we currently would describe as a black hole solution, but at that time, Einstein himself didn't believe that that could be a real thing. Einstein was pointing out that probably there is some mathematical weird thing happening, and it's probably not really like that. We are missing something. It's too weird to live. It's too weird to happen in reality. There was, very soon after, there was a sort of a confirmation of this solution of Schwarzschild, which kind of gave a little bit of credibility to these conclusions. And this was related to measuring the deflection of light rays coming from the distant stars, deflected by the sun. So general relativity predicts that light should be bent, should be deflected by the mass of an object such as sun. Here it's exaggerated greatly. This difference is really counted in angular seconds. So it's really, really tiny difference. And it turns out that Newton and Einstein predicted different values of this deflection. So there was this test in a weak limit, because the gravitation of sun is nothing like the gravitation required to form a black hole. But there happened this confirmation, and that was done in a very, I would say, romantic way, because Arthur Eddington and other scientists had to go to a remote place, St. Thomas Island near the coast of Africa, and a different island in Brazil. And they had to go there during the total solar eclipse, for the reason that this is the only time when they could see the rays from the stars that would feel the gravity of the sun. Of course, during the day, stars are there, but sun is too bright for us to see those stars. So total solar eclipse is the only moment when you can see the stars that are close to the location of the sun in the sky. And that was a great success. This operation, this observation confirmed that general relativity works, but in this very weak limit. So this added a little bit of credibility to the Schwarzschild solution, but people were still very hesitant to say that something that works for this very small weak gravity, that it could be extrapolated into conclusions about this very, very strong gravity of an object such as black hole. So people for many, many years didn't really believe that those black holes could be something formed in reality. It changed through a couple of discoveries in 1960s, and I will talk about two such discoveries. First one is a theorem that was proved by Roger Penrose. And this is a theory that showed that singularities actually can form in quite general conditions. I'm speaking in vague terms because this is all formed in the complicated language of differential geometry. However, this solution gave a lot of credibility to the claim that singularities and black holes could form in realistic conditions, that maybe it's not a weird mathematical trick or something wrong with the equations, and there would be no way to form such an object. So this is the theorem for which Roger Penrose received a Nobel Prize in Physics earlier this year, just a couple of months ago, if you recall. There was another argument for the existence of black holes. Pretty much in a similar time, in the 1960s, people noticed that there are sources in the sky that are extremely bright. They look like stars, so they clearly are compact objects. But people noticed that they are actually very far away. Through analysis of their spectra. So what it meant is we have something that is as bright as a nearby star, but really is located billions of light years away from us. So this is something that must be extremely strong. And the argument was that, well, you couldn't get something like that from a star, but perhaps you could get something like that from a black hole. So notice a little bit of a paradox, because we talk about black holes as something that is black, no radiation is coming out of it. But then now we are talking that there are extremely bright objects in the distant locations in the universe that are so extremely bright that they can only be black holes. So there is a little bit of problem here. The reason why we think that those objects are so bright and they are black holes is actually that when black hole interacts with its vicinity, when matter falls onto a black hole, we call this process accretion, it is releasing a huge amounts of energy. And how should you think about it? Why does it emit so much energy? Just think about a following experiment. You climb a very high tower, and you have something heavy, and you just throw it from this tower onto a pavement below. You can imagine what will happen. This thing will create a sound. To create a sound, it means to create a mechanical wave. It requires energy. It will maybe break this pavement. So it means that this ball that you have thrown, it received a lot of energy through the gravitational field, because it accelerated in the gravitational field. So now imagine that you are not throwing something onto the surface of the Earth from a high tower. Instead, you are throwing something into this very, very compact, very, very gravitationally strong object that is a black hole. It will convert a lot of gravitational energy. There is no pavement to hit near the black hole, but there is a different mechanism. This energy will be radiated away. So this hot gas swirling around the black hole, it will become extremely hot, it will become ionized, and it will start shining. It will be radiating, and it will be radiating an extreme amount of energy. How much? You can see this equation here. You may remember the famous equation of Einstein, E equals mc square. This is the total rest mass energy of an object. So this is as much energy as you could possibly extract from an object before you give it kinetic energy. And you see that it's about 10%. It can be more, it can be less. It's about 10%. So you may think that 10% is not much. So let's compare it to something more familiar to us. Something more familiar to us would be burning coal. So this is the efficiency of burning coal. You see there are quite a number of zeros here. It's much, much less effective than receiving energy, creating energy by throwing things into black holes. The picture you see to the left is the artistic vision of how such a system looks, the system that converts energy from gravitational into radiation. So this is a gas that is forming a disk and is slowly falling onto the black hole while emitting the large amounts of radiative energy. Right, so we currently think that there is a supermassive black hole in the center of every galaxy, or most of the galaxies. Some of them are feeding on a lot of matter. If they are feeding on a lot of matter, then they become extremely bright. Some of them are kind of starving. But those who are feeding on a lot of gas, those can create huge amounts of radiation. So now we are almost done with our physics lessons. There is one more thing to bring up. How is this radiation emitted? What process is responsible for the emission of radiation? There are multiple processes that can be responsible, but I will be talking about the one that is relevant for M87, and this is called synchrotron radiation. So this is something that requires magnetic field. If there is a magnetic field and ionized gas, so electrons and protons are separate, then accelerating protons and accelerating electrons, what they will do is they will be gyrating, this is how it's called, turning circles around the magnetic field lines, and through acceleration, they will be radiating some energy away. This is called a synchrotron process. So this is something that requires magnetic fields as well. So we need a hot ionized gas, and we need electric fields, magnetic fields. And then we will produce a lot of radiation coming from the vicinity of our black hole. So I've mentioned bending of the light associated with the star, and I said that it's just it's a small deflection. It's only of order of seconds of arc. So now this is how we believe, how we calculate how things happen for the black hole. So now you see that those light rays are not deflected by a couple of minutes. This one that you have seen a second ago, they actually made a full circle around the black hole. So it's a huge deflection. It's 10,000 times stronger about than the deflection of rays from stars because of the presence of the sun. So we are talking about very different, very strong regime of gravity. And you also see that when those rays were forming this image became much larger than the Schwarzschild radius of the black hole. So this corresponds to the Schwarzschild radius. And you can see the Schwarzschild radius, and here the outline of a black hole is much larger. It's larger by, you can calculate that it's larger by square root of 27, which is 5 and a little bit. And this is all because this very strong deflection of light near the black hole. So this is what we are after. This is what we expected before making the observation of the EHT, what we would expect more or less to see. Okay, so now you are experts in general relativity and physics of accretion and physics of magnetic fields near the black holes. And now we can go and become experts in engineering. So now I will talk a little bit about the Event Horizon telescope as mankind's highest resolution camera. I will start by showing you an animation about M87. This animation will have dramatic music. If it will be too loud, I will try to turn it down a little bit. And this is the movie. I will turn it down. This is the movie showing where is M87 on sky. M87 is a galaxy that you can actually see from Prague on a very good day when the light pollution is not too bad. So maybe from the suburbs of Prague rather from the center of Prague. And you can see it with binoculars, but you will see only this little cloud similar to the image that that Vladimir was showing. So that's how much you can see with binoculars. But if you have a radio telescope, you can zoom in. And that's what people were doing for many, many years. People were zooming in with more and more sophisticated radio telescopes and with shorter and shorter wavelengths until last year we got to such a good resolution that we saw this pretty donut. So let's talk now about this resolution. What kind of resolution do we actually need to take an image like that? So in order to know what resolution we need to know how large is the object and how far away from us it is. So M87, this supermassive black hole in the center of M87 is actually a huge one. It's very heavy. It weighs 6.5 billion solar masses, and it's actually larger than our entire solar system. So it's a really, really huge black hole. But also, it is quite far away from us. It's about 50 million light years away from us, which I said it's far away. It's not far away in cosmological sense. Cosmologists would still consider that to be our neighborhood, our cosmic neighborhood. Nevertheless, 50 million light years is quite far away from the point of view of how large this object is. So if you calculate how a black hole of this size, how large should it be in sense of angular size, at this distance, you will get that it will be just about 40 microarc seconds. Is that a lot? Well, it means that it's 40 million times smaller than the full moon. So if you take an image of full moon, you have to divide it by 40 million, and then you will see how tiny this feature is in sky. So there are a couple of colorful comparisons of what this great resolution required, what is it equivalent to. And one thing I like is to tell that this is just like watching a snooker or billiard or pool game that is happening on the surface of the moon, and we are observing it from the Earth. So if you could still keep track of the score, then it would mean that you have the resolution just as good as to see M87. Then you can also say that, well, it's maybe the same as seeing a little fruit like orange from Earth, the orange that is located on the moon. Then you can also think about reading a newspaper and some tiny fine print while sitting in Prague, and the newspaper is opened in New York. So that would be also another example. Or you can think about seeing a single atom from 1 meter distance. So these are all, if you have another interesting idea of equivalent resolution, I'm very interested in learning what you think. Okay, so in 1970s, a very famous astronomer, James Bardeen, calculated how this outline of a black hole, this a feature that we are calling the shadow of a black hole, how it depends on the rotation of the black hole. So it changes a little bit with how fast the black hole is rotating. And he made this claim that, well, it's maybe interesting if you could see that feature, but unfortunately, there is no hope of observing this effect. So he said that in 1973, and he was almost right because it took almost 50 years, over 40 years, before we were actually able to see this feature. Now, a little bit of uncomplicated math that you are probably also familiar with as people interested in photography. There is a fundamental limit to the resolution. This is called a diffraction limit. So your resolution can be as good as wavelength at which you observe divided by the telescope diameter. So it has equivalent for the photography with the wavelength corresponding to the optical light wavelength, and telescope diameter corresponding to the size of the your lens. So we need, this object is of the diameter of about 40 microarc seconds, as you see. So we need, let's say, 20 microarc seconds to really resolve it, meaning we don't want just to see that it's a blob. We want to see some details of it, like maybe there is a shadow in the middle. So we need to do a little better than 40 microarc seconds in order to get there. And this means that if we use 1 millimeter wavelength, that we need a telescope of the size of 10,000 kilometers. Now, 1 millimeter is very difficult. It's very short, and radio astronomers cannot deal with the shorter wavelengths for now. This is mostly related to the terrible behavior of the atmosphere that is messing up everything. So it's worse for shorter wavelengths. So if we use the shortest wavelength we could possibly think of, which is 1 millimeter, then we would need 10,000 kilometers. 10,000 kilometers is about diameter of the Earth. So our telescope would have to be a diameter of the Earth. And that is complicated. How do you get a telescope of the size of the Earth? So my idea of how this telescope should look like was this, but this wasn't approved by any agency that is distributing money. So we weren't allowed to build a telescope, turn entire Earth into a single telescope, unfortunately. So the next best thing that you can think of, and what you could do, is instead of doing that, you could think about using a technique called interferometry. And this will be a little tricky to explain what's going on, but I will try to give you at least some kind of notion of what interferometry is doing. The clue is that you need at least 2 telescopes or a number of telescopes, and the measurement will happen between this pair of telescopes. So we need to record the source at the exactly same time. It needs to be so exact that you do need an atomic clock to synchronize them. And then you can numerically bring them together. So really it is like entire Earth was your radio dish, but the only 2 active pieces of this dish were those 2 remote telescopes. All the rest of the dish is broken, it's not working. It's only these 2 little points that are giving you anything. But we had more telescopes than that. In 2017, EHT observed M87 with 7 out of 8 telescopes that are participating in the array at 5 different geographical locations. And there is another trick that we are playing with the radio interferometry. Now I can reveal the name of this technique. It's called very long baseline interferometry. And it has a trick that is called the aperture synthesis. And this is actually something for which Martin Ryle got a Nobel Prize in Physics in 1974. He was the first one to actually perform this sort of observation and to prove that this concept works. And the concept of aperture synthesis is extremely simple. I will play that. The concept is that Earth is rotating during the night of observations. The source is standing still because it's a huge black hole. It doesn't change during one night. For such a huge object, it takes time to change. So it means that as the Earth is rotating and the geometry between the telescopes and the distant object is changing, you are looking at the object at slightly different angle, at slightly different geometry. And for that reason, you are able to synthesize more aperture. I will not give mathematical details of that, but these guys here are called spatial frequencies, and each of them corresponds to the location at which you make a measurement related to the appearance of the object. And there is a more simple explanation that I will try to give you now. So bear with me for a minute. I will explain how radio interferometry works based on ducklings sitting on the pond. So imagine you see those ducklings, and they can do what ducklings are doing. So they are just sitting there, they're splashing water, they are just being active. And depending on are they close to one another? Are they more distant to one another? They will create different patterns of waves. So these guys here will look like that. These guys here will look like that. Those waves will interact with one another. And you see that the pattern of the waves is different. So then, I will replay that. So then you can think about, how do I detect those ducklings? How do I say where the ducklings sit? Well, you can team up with a bunch of colleagues. You can ask them to go around the pond and to take measurements of the waves at the edge of the pond. And then you can compare this measurement between you and your colleague. And you can ask, okay, so dear colleague, if you move a little bit to the right, is the wave still similar as I am seeing, or is it very different? So this we would call a coherence length. Here you see there is a long coherence length. The wave is similar here, and here it changes quickly. So in this analogy, ducklings correspond to some astrophysical object. The people making measurements of the waves at the surface, at the edge of the pond, they correspond to our telescopes, and the measurement is really a comparison between one and the other. So this is why we need to record one measurement at one telescope, another at the different telescope, and we need to compare them. It's kind of useless to have only one telescope doing that. So this is the slide about what we do to the data before we are able to image it. And I usually spend most of my talks at this slide, but I will only play it and give you extremely brief description. So we record the data. The data is huge. We cannot send it through internet because it's too much data. So we put it on an airplane. We fly it to a location where it's correlated, and the correlation is this comparison that two people are doing between the wave that they have measured. Then in another step, we have to deal with the turbulent atmosphere, and this requires some more sophisticated algorithms. And finally, we can use this data to compute the image. This is computational imaging. And as you see, along the way, we record about 5 petabytes of data. Then after the correlation, this first step, we only get terabytes of data. When we go to megabytes of data after the calibration, this is because we can average data more because it's behaving in a more stable way. And finally, the image is really created for only kilobytes of pure information. And this is, I try to highlight a lot of problems, technological challenges to make this measurement, to make this observation. And this is the reason why we need a large team. There are over 200 people contributing to the Event Horizon Telescope because we need engineers to design hardware that is able to address these huge problems that we have. Then we need people being able to reduce the data. Then we need people who are specialists in reconstruction of the images. And then we need theorists who would tell us the interpretation of what is it really that we are seeing. So it takes a lot of people to do all of that. So now, finally, we are experts in both physics and engineering, and we can move towards the direction of philosophy, but also photography and what photography is. So let's start by looking at this pretty image, and let's find a couple of features that we can try to understand. So here in the middle, there is this dark part. So our interpretation is that this is exactly because nothing can escape the event horizon. So this inner part will remain dark. Then we see a bright ring around because there is stuff around the black hole, and this stuff is emitting radiation through the synchrotron process that you are now familiar with. So there is a hot plasma and it's shining through the synchrotron process. And it's brighter in the bottom because we think that this is accelerating in our direction. I will explain it with a donut. So there is a black hole in the center, and there is this gas around that is in the form of a donut. So this is a donut. There is a black hole inside, in this place inside the donut. And we think that M87 is actually located something like that. So it's rotating the way this image is showing. So it means that the bottom of this donut is going in our direction. It has velocity in our direction. And this is something that through something that is called Doppler process, which again, this is something that many of you could have heard about in high school, for instance. But because this is approaching to us, this is brighter. And this top side of the donut is darker because it's going away from us. So now I will try to give an answer to a philosophical question about could we ever see a black hole? Well, my approach to that will be extremely, extremely primitive because I am, as you see, I am showing you a hole in the ground now. There is a reason why it makes a lot of sense to say that we could never see a black hole. Of course, because there is nothing that can escape event horizon. It means that light cannot escape event horizon. It means that we cannot see an event horizon. But then you could actually, in my opinion, make a similar claim about this hole in the ground. If you ask, can I take a photo of a hole in the ground? I don't think so. What can you see in this photo? You can see grass and you can see a circle of dirt in the middle of it instead of grass. Where is the hole? You cannot see hole. You can see the environment that is surrounding the hole. So this is, in my opinion, a little bit similar point, but I would be very happy to hear your comments about, do you think that it is an image of a black hole if you see the interaction of this black hole with its surroundings? And now I will briefly go through people write books about that, people like Peter Garrison, but I will summarize it in just a couple of slides. I will talk about the meaning of image in natural sciences and how it changed throughout centuries. So I will not start from the beginning, I will start from the 18th century. So in 18th century, the vision of a scientist was that it's a wise man who knows pretty much everything. He has access to understanding of some Platonic ideas of the objects that the scientist is observing. So if he is making an image, a scientific image, and the image he is making is of an object that is not a Platonic idea, then the scientist should intervene and should make a corrections for this image to be to be representative of this Platonic idea. And I will give example for that approach. Then in 19th century there was a radical turn, and scientist was no longer a wise person. Sorry, now scientist of 19th century is a worker, and the image is a mechanical thing. And imaging, drawing images, is a mechanical transfer. No intervention should take place. You should draw exactly what you see, and you shouldn't be making some sort of generalization, and you shouldn't be looking for some Platonic ideas. Then in 20th century, we have something in between. Scientists are now experts, and they can make alterations to the image, but they have to be justified. There need to be some judgment behind that. Now I'll just quickly go through examples. So Johann Goethe was not only a very important person in the history of literature, he was also very interested in natural sciences. And he had this, I would say, maybe obsession is a strong word, but kind of obsession with finding an archetypal plant, the plant from which all other plants can be derived. And it was called flanzer. Of course, he never found an example of such a plant, but he had this idea, and this is what he depicted in his drawings. He looked at many plants, but then he tried to draw a plant that is the essence of all other plants. It sounds a little weird for 20th century sciences, but that was the approach this 200 or so years ago. Then in 19th century, we have this workers' approach to imaging. So for instance, here we have Otto Funke, who created a lot of images about anatomy, about cells, seen through microscopes. These are the crystals of blood that you see here. And you can see in this side of the image, it's a little different color than here. So this is actually a chromatic aberration. This has nothing to do with the biology. And Otto Funke knew that very well. But nevertheless, he drew this chromatic aberration because he felt like he cannot alter the image. What he sees needs to go into the image. He cannot make alterations, even if he knows that it would make sense to make those alterations. So we're almost done. We are at the stage of 20th century, and the modern approach to images of an expert who is making alterations. So I'm pretty sure you have seen Hubble Space Telescope images like this image of Eagle Nebula. And you probably saw the colored version. So I have to disappoint you, unless you already know that all those colors are made up. Hubble Space Telescope is only sensitive to the total intensity of the image. So the right image, unfortunately, is that. This is what Hubble Space Telescope can give you. But then the scientists behind it believe that it makes sense to use their best knowledge and understanding of the processes to make the images with colors. So they are made up, but not really made up but by someone who has no idea. They are made up after a careful examination and consideration by scientists. And I will give just one more example on this slide. This is a Curiosity rover, but who took this picture? This is on the surface of the Mars. This rover is exploring Mars, and somebody clearly took a picture of it, and you cannot see this person. So is this made up? No, it's not made up. This is a composition image. So what this robot has, it has an arm with a camera, and this arm can go around it, and it can make multiple images that then you can stitch into a single composition image. You need about 70 images to make an image like that. They are all from different angles, so they are tilted in different way. And in order to stitch them together, you not only need to move them around, you need to apply some mathematical transformations to stitch them. And of course, at no place, the camera will take a photo of itself. So this is why you cannot see the arm with a camera in this picture. So if Otto Funke would see this image, he would be shocked and very disappointed that, well, this is some mathematical operation of the images. This is something unacceptable. And of course, Goethe will be unhappy because it's clearly not a Platonic idea of a Mars rover. This is some particular Mars rover that happens to currently be on Mars. And Goethe would probably like to have a Platonic idea of a Mars rover. It's getting more complicated. If you consider magnetic resonance imaging, now we are talking about really something that we call computational imaging. So this is a standard medical procedure right now. I'm sure many of you had a magnetic resonance in one point or the other. But do you know how it works? The way it works, you put your head or some other part of your body inside a magnet that is very strong and is very quickly changing. It's oscillating. So these oscillations are exciting the different molecules in your body, different atoms of your body. So they are getting excited, so they wiggle around, and they start emitting radio frequency radiation. So when there is a detector of this radio frequency radiation, and because different tissues in your body are responding differently to the quickly emitting excitation, it can differentiate between one tissue and the other issue. But it's not the end of the story. You really measure, by that mean, you measure a slice of the image, and not even a slice, you measure the behavior along a single line. So then you need to combine all those lines, and you can use the mathematics of so-called tomography, this mathematical procedure. I will just use a name here. It's inversion of so-called radon transform. And then you mathematically compute this image, and then from combining these mathematically computed images, you create a three-dimensional scan of a piece of your body. So the question is this a photograph? Could you say that this computational imaging is still a photograph? Well, I'm very interested in what you will tell me, because you are the experts on photography. But my argument here would be that from origin of the word photography, photography means drawing with light. Radio frequency is light, and this is clearly a drawing. So I would say maybe you could call this sort of procedure photography. But again, I'm really interested in what you would tell me. So I'm almost done. I will just give a couple final comments about this, well, star of this talk, which is M87, or a black hole of this talk, maybe not star of this talk, a black hole of this talk. So an important thing to notice is I mentioned that we are using 1 millimeter radiation. This is not optical light. This is radio frequency. So what does it mean that it has an orange color? It means nothing. We have only chosen this orange color. Really, well, first of all, we are only sensitive to total intensity, just like Hubble telescope. So we don't have information of colors, meaning we don't have information of different regions of the spectrum, but also, like, why would you attribute this color and not the other color to a radio? What is the color of the radio frequency radiation? We have had to make a choice, and we have chosen this pretty orange color for the reason that it brings the idea of this object being very hot, and this plasma is very hot. It's billions of kelvins. I will mention just very quickly a couple of other problems or issues with the image and how objective it is. Well, there is such a thing as perceptual uniformity of a color map. So if you choose a color map by random, it will have particular places that seem to be more prominent, meaning you will see that there are features, like I'm pointing features with my cursor here, but it's not a real feature. It's just the artifact of a map, of a color map. So one thing we did, in order not to suggest to people that there are some features in this image that they are not really there, we have designed our own color maps that are perceptually uniform, meaning they should have no characteristic features. When you look at the bottom plot and not at the top one has features. And there is a couple of more issues. Of course, this is computational imaging. It's not a direct photography. And then this computational imaging is kind of, it doesn't know what kind of blurring to use. So we had to decide how much to blur our images. And we have made this decision through a discussion of what features can we be certain and what features are so uncertain that we should just blur them out. And these are some examples of images that are not blurred, obtained through different imaging techniques. So here is different days of observations and couple of different imaging techniques. Now nothing is blurred, but you see one technique is giving you kind of less sharp features, the other technique is giving you more sharp features. So we decided to go with the lowest common denominator, or largest common denominator, well, depending in which direction you look at it. We decided to go with the lowest resolution provided by any of these methods. So we combined them into a single image. And this is the example of this 20th century, actually 21st century approach. So there were a lot of choices to be made in how we present this image. And these choices were made through a lot of discussions between the scientists. And well, you can believe me, where there are two scientists, there are usually three opinions. So now imagine over 200 scientists by the same mathematics, it's over 400 different opinions, which means it's really difficult to, to find make a common decision about how this is being presented. Nevertheless, we had to do something, and that's what we did. And I think the feature of the modern science to stress at this very, very end of my talk is that, well, of course, all the data and all the methods that we used are public. So everybody is welcome to make a comment about how it is presented. And all the scientists can comment that, well, maybe you should do it differently, and they can write their own research based on that, and they do. So this is an element of how science, open science, works in 21st century. Okay, so I will leave you with this image, and thank you very much for the attention. I don't think we lost too many people, so maybe I wasn't speaking in too difficult terms. Thank you very much.